Everybody got a different version of me. Everybody gotta be learning from me. Everybody wanna be working with me. And I feel like there's uncertainty and urgency to find out what you wanna be. But honestly, we change our minds constantly, so stop and breathe to find out who you wanna be. Failure ain't an option, so I'd be cautious. I hope that you're watching. Don't try to stop this, work until I'm nauseous. Cause I will not quit, no, because I want this. Don't try to stop me, failure ain't an option, so I'd be cautious. I hope that you're watching. Don't try to stop this, work until I'm nauseous. Cause I will not quit, no, because I want this. Don't try to stop me now. Me, I don't give a fuck if you got a college degree. Did you learn anything really worth it?
Good afternoon, everyone. Selamat siang, rekan-rekan peserta, serta Bapak Ibu dosen yang sudah hadir. Welcome to the waiting room of Chemistry Advanced Studies Exploration #2. While waiting for other participants to join the Zoom room, please make yourself comfortable. We kindly request all participants to adjust their Zoom display name using our official format, which is agency_your full name. And don't forget to use our official virtual background also. So today we are going to talk about something very exciting about photochemistry and visible light mediated transformations. The title itself is very beautiful, Beyond the Ground State, when molecules catch the light. So brace yourselves for a very insightful session today. Maybe I would like to greet our speaker initially. Good afternoon, Mr. Basso.
Hello, can you hear me?
Professor Basso? Yes, I can hear your voice very well. It's
Thank
a
you.
such pleasure to meet you today. How are you?
I'm fine, thanks.
Very grateful to meet you here. Okay, so it's a warm Monday afternoon. We have many enthusiastic participants here who are very eager to listen to your lecture. So, Professor Basso, we will officially start the agenda in about a couple of minutes. I will open the session in English, introduce you briefly to the audience, and then the time will be yours for the presentation.
Very good.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and welcome to all of us. We are honored to have our guest speaker today, Professor Dr. Andrea Basso from the University of Genoa, Italy, as well as all the participants who have taken the time to join us this afternoon. Welcome to the Chemistry Advanced Studies Exploration #2 with the theme Beyond the Ground State When Molecules Catch the Light. Please allow me to introduce myself. I am Gavriel Sumlang, a doctoral student at Universitas Gadjah Mada, Indonesia, and I will be guiding today's webinar. We would like to thank you all for your presence, as well as the participants who have joined us for this session. We hope that through this event, we can expand our knowledge regarding the application of photocatalytic technology within the framework of energy transition and green chemistry, as well as structural modification of photocatalysts. Our lineup of activities this afternoon consists of an opening, a brief introduction of the speakers, presentation by the speakers, followed by the Q&A session, a conclusion, a group photo session, and lastly is closing remarks. Before we begin, I would like to inform you that an attendance link will be shared at the end of the session. So participants are requested not to leave the Zoom room until the event concludes. Certificates will only be distributed to participants who complete the attendance form. All right, ladies and gentlemen, and everyone here, let's begin case #2 with a prayer that today's event goes as planned. Please say your prayers. Prayer concluded. Well, before we commence today's main session, let me introduce our distinguished guest speaker for today's session. He is Professor Dr. Andrea Basso, a prominent expert in the field of synthetic organic chemistry. Professor Basso is currently a full professor of organic chemistry at the University of Genoa, Italy. He earned his PhD from the University of Southampton and further expanded his expertise through international postdoctoral positions in Halle and Basel. Throughout his remarkable academic career, he has authored 15 books and approximately 140 peer-reviewed papers in international journals, garnering over 4,000 citations with an Hurst index of 37. His specialized research focuses on multi-component reactions, diversity-oriented synthesis, and batch or flow photochemistry. His innovative contributions to the field have been recognized with prestigious awards, including the Italian Chemical Society Prize for Research in Organic Synthesis and the National Consortium CINMPIS First Prize. Furthermore, Professor Basso is a proven leader. He has served as the coordinator of chemistry degree programs and is the current president of the Ligurian section of the Italian Chemical Society. He also plays an active role in scientific publishing as an associate editor for Frontiers in Chemistry and successfully manages continuous R&D collaborations with prominent industrial partners such as Merck and Roche. It is an honor for us to have the opportunity to learn directly from him today. To all participants, if you have any questions, please type them in the chat box during the presentation or ask them directly during the Q&A session. Without further ado, Professor Dr. Andrea Basso will now present his presentation, which will last for 60 minutes. Excuse me, Professor Basso? Whenever you are ready, you may prepare your slides for sharing screen.
Yes, I like to share. I sent you a request to share my slides.
Okay. Wait a minute.
Yeah. Okay, should work now. Can you see my screen?
Okay, still loading. Okay, we can see your screen. Okay, so thank you, Professor Basso. Please join me in welcoming Professor Dr. Andrea Basso. The time is yours.
Thank you so much. I don't see your screen, so do you see the presentation in the presentation mode?
Yes, we can see it. Or
Okay,
yeah.
because I do have in the oh, okay, now it should be okay. You can see it?
Yes, Professor.
Okay, so thank you
Can
very
see.
much for your kind introduction, and it is a pleasure for me to be here for this lecture. I thank you all the organizer for giving me this opportunity to have some exciting, as you mentioned, knowledge about photochemistry, and the word excitement is not by chance, because exactly we will talk about excitement of molecules. So let me start just with a brief introduction. My city where I perform research is Genoa, that is here. Let me choose the pointer. That is in Europe, in Italy, and in this part of Italy. This is on the sea. And in Genova now is 9 a.m. So good afternoon to all of you, but in my case it's good morning. And Genova is on a sea town because it's on the coast. It has a very famous harbor, and this part of the city was rebuilt in 1992. So 500 years after the discovery of America by Christopher Columbus, because indeed Christopher Columbus came from Genoa. So he is, I would say, the most famous Genoese person known in the world. So let's move from Genova to photochemistry. Genova is somehow a sunny city, especially during these days. We have about 28 degrees, sunshine, and so it is the perfect time to perform photochemistry. When we talk about photochemistry, we talk about chemistry, so transformation of substances. And if we want to transform a molecule, for example, in another, using light, we need to use specific wavelengths. So when we talk about photochemistry, usually we talk about only a narrow part of the electromagnetic spectrum, that is the ultraviolet region and the visible region. So we are spanning between more or less 200 nanometers and 800 nanometers. So a very narrow region, but this region has many potentialities. Of course, not all, not saying that the other regions of the electromagnetic spectrum are not important, because, for example, radio waves are essential for NMRs, and we, as organic chemists, know how important is NMR in our everyday life in the lab, but the energy that is associated with visible and ultraviolet light is extremely important when we want to perform reactions, because when we use this radiation, we can interact with the valence electrons, and the valence electrons are those that are important for transformations. You probably are aware of the Jablonski diagram that somehow can be considered as our starting point, because we cannot talk about photochemistry without some knowledge about photophysics. And when a molecule is able to absorb light in the visible or ultraviolet region, what happens is that the valence electrons are excited from a ground state to an excited state. And then, from a photophysical point of view, the evolution of the system can be going back to the ground state through fluorescence processes, or maybe if the molecule is able to give an intersystem crossing that very simply is inverting the spin of the electron that has been excited, then in this case you have that the system evolves from a singlet to a triplet excited state. And from a triplet excited state, again, from a photophysical point of view, you can have phosphorescence that, as you can see from this slide, is much slower because, of course, in order to move back from the triplet state to the ground state, you need another intersystem crossing. So you need, again, that your electron inverts its spin. We will be back, we will come back to these triplet states because the triplet states are essential for photochemistry, because the fact that the molecule survives for longer times in the excited state when the molecule is in its triplet state gives chance to have also reactions, not only photophysical processes, but also photochemical ones. But I would like to stress a few things about what do we mean for photochemistry and why photochemistry is so important and interesting. So we have some features here that we can analyze. Basically, in the top part of this slide, you have the simple representation of a thermal reaction. When you perform a thermal reaction, even if the products have a lower energy than the reagents, and therefore, even if from a thermodynamical point of view, the reaction is favored, still you need to give energy to your system in order to convert the reagents into product, because you need to reach the transition state. So you need to give to your system activation energy. And depending on the height of this maximum, you might have reactions that can be slower or faster. For example, one typical case is the one of diamond and graphite, because from a thermodynamic point of view, graphite is more stable than diamond. So in principle, diamond could be easily converted into graphite. So a nice ring into a pencil, that would be terrible, of course. But luckily, the activation energy for this transformation is very high. So if you have a diamond, you can keep it for, there is a spot in Italy that say a diamond is for all life. Indeed, you can keep your diamond without getting a graphite for your whole life. So the typical thermal chemistry is related to this sort of profile. And in the lower part of the slide, you see another example of a thermal reaction, in this case with the formation of an intermediate, of a reactive intermediate, and then the formation of the final product. You can facilitate the process, for example, by using a catalyst, because by using a catalyst you can lower the energy of the transition states and you can make the process faster. But still you need some activation energy. Now let's move to a photochemical reaction. In a photochemical reaction, the molecule is excited by the radiation, by the interaction of the radiation. And from the excited state, the profile of the reaction, as you can see, is almost always downhill. So you do not need anymore an activation energy, because the activation is light itself. So, important things that we need to take into account when we talk about light-mediated reaction is that usually, not always as we will see, but usually they are UV-mediated. So it is more easily to reach the excited state by using more energetic ultraviolet radiation. Obviously, this approach is limited by the availability of molecules that can interact with light. We will see and we will analyze these aspects later on. And then one very important thing is that once you create the excited molecule, as again we will see in a few slides, the chemical and physical properties of the excited molecule differ greatly from the ones of the original molecule. And this is essential for the chemical transformations. Which kind of chemical transformation can we talk about? Well, then there is a number, because we can have, for example, that an excited molecule can fall apart and generate a new structure, can combine with other molecules on the ground state, or can transfer electrons, hydrogen, protons, or even other atoms to another molecule. So all these possible paths are related to the different photochemical reactions that we can perform once we reach the excited state. In this slide, we see some of the properties of simple molecules that are described both in the ground state and in excited state. Let's take, for example, hydrogen cyanide, a very simple molecule. What happens when we excite hydrogen cyanide? Basically, the most striking feature is that the molecule of hydrogen cyanide that is linear in the ground state becomes angular in the excited state. So you completely change the shape of the molecule, but also the distances of the bonds, carbon-carbon-nitrogen or hydrogen-carbon bonds, becomes longer, and this obviously changes the chemical properties. Let's take another simple molecule like formaldehyde. We know that in formaldehyde, the carbon atom is sp2 hybridized, so the molecule is planar. This is something that you get as an information in the first undergraduate year, in the first organic chemistry course. But if you excite formaldehyde with UV radiation, you get a new molecule that is no longer planar, but is pyramidal. Let's move to another aspect, that is acidity of the molecule in the excited state. Usually molecules in the excited state are more acidic and have a more powerful oxidant power. So let's take, for example, phenol. We know that phenol has a pKa in the ground state that is about 10. But if we take phenol in the excited state, the acidity becomes similar to the one of a carboxylic acid. And let's take a more complex molecule. We will talk about these molecules later on during this presentation, like this ruthenium photocatalyst. In the ground state, you see that the reduction potential is negative, but in the excited state, it completely changes and becomes positive. Something that maybe is less important, but still quite interesting, if you take an aromatic compound like 1,nitro,3,4-dimethoxybenzene, if you want to perform a nucleophilic attack on this molecule, replacing one of the two methoxy groups with an OH group, so changing from methoxy to OH, and you perform this reaction in the ground state, the most probable event is that the methoxy group in the 4 position is displaced by hydroxy group. But if you excite this molecule and then you perform the reaction on the excited molecule, then the most probable displacement is the methoxy group in the 3 position. And so, I mean, I could continue with this list of properties that dramatically change from the ground state to the excited state. But I mean, it is not worth going on with this, but this is just to make clear that the molecules that reach the excited state can react completely differently from the same molecules in the ground state. Now, let's stop for a moment on the scientific part, and let's focus a little bit the nature of photochemistry with some historical aspects. I always like to give some historical information about what we are talking about, because chemistry is an evolution of information, and throughout the centuries we have gained a lot of new information, a lot of new techniques, but it is important not to forget what was done at the very beginning with the instrumentation, for example, that was available in the 19th century. So in this slide you see three different old-fashioned people, and we will these three scientists play an essential role in the evolution of photochemistry. So the photochemistry that we know now is available because of the studies of these three people. Not only them, we have many more players of photochemistry in the history, but I selected the three illustrated here. The first one because we can consider him as the one who really started to study photochemistry, and the other two that are both Italians, because the first one is considered as the prophet of modern photochemistry, and the second because he discovered one of the most useful photochemical reactions. But let's start from the first person, that is Hermann Tromsdorf, that was born in Germany in 1811 and died in 1884. Why we consider Hermann Tromsdorf as the beginner of photochemistry as we consider it now? Not because he was the first one who realized that light and matter could interact, because before Tromsdorf, other important scientists like Priestley, like de Bruijner, discovered that it was possible to get transformations using light, transformation of molecules using light. But Tromsdorf was the first ever that realized that the wavelength of the radiation was somehow important for the transformation. He was the first who decomposed the white beam of light into the different components, as taking the words from his lab book, that was written in Germany, of course, but just to translate it, he discovered that this molecule here, that at that time was quite important as a drug because it was used as an anthelmintic, he discovered that this drug, when exposed to light, decomposed. But the first example of how we consider photochemistry at the moment was that he decomposed the light in the different components, and he found that only the blue and the violet radiation, so the more energetic one, was able to induce this decomposition of santonin, while yellow, green, or red beams were not able to do so. So he realized that there was a direct correlation between the reactivity of the molecule and the wavelength, frequency, energy of the radiation. The second person we want to talk about is Giacomo Ciamician, Italian. He was born in 1857 and he died in 1922. He was a professor of general chemistry, organic chemistry, biological chemistry. Not only, he was only a city councillor and a senator of the Italian reign. But the most important thing we remember him for is, apart from his photochemical studies, the fact that he was the first who proposed alternative energies such as solar energy to replace the fossil fuels. And I will conclude then this lecture with some of his words. In this picture, in the bottom, you see Giacomo Ciamician with his assistant, Silber, who performed reactions in the University of Bologna. The Department of Chemistry of the University of Bologna in Italy is now called Dipartimento Giacomo Ciamician in honor of this prominent scientist that realized that many transformations could be induced by light, and at that time the most easy way to perform these transformations were to go on the roof of the chemistry department and use these glass vials with solutions of reagents to perform the reaction. It is interesting to read the lab books of Giacomo Ciamician because nowadays such a research would not be possible with all the frenzy we have. The lab book was saying that on May of 1901, the flask with toxilic acid was placed on the roof, and then 1 year after, the reaction was analyzed and the transformation of toxilic acid was determined. So it took, let's say, 1 year for a transformation to take place at that time. Obviously, nowadays everything is much faster. The third player that we talk about is Emanuele Paterno, again an Italian chemist. He was born in 1947 and he died in 1935. He was the founder of the most important chemical journal in Italy. Nowadays this journal is no longer existing, but we have a European journal that combines all the European journal societies, and the journal was named Gazzetta Chimica Italiana. But it is not for this that we remember him, but for the fact that he discovered the reaction that was taking his name. Actually, the reaction is called Paterno-Bucchi reaction. We have a second name. We will see why in a few seconds. But the Paterno-Bucchi reaction is a very powerful reaction because it can generate oxetanes, so 4-member rings with an oxygen in the ring itself, just by combining a carbonyl component and an alkene. So just by joining in the presence of light these two molecules, you can obtain a 4-member ring, something that is quite difficult to achieve with other synthetic paths. And as we will see, we will we see how, for example, there are many natural compounds that possess this 4-member ring. The possibility to generate it so easily just by shining light on an aldehyde or a ketone and an alkene is a very powerful advancement of this chemistry. So let's go, complete this digression on the history of photochemistry, and let's move again to reactions. A molecule, in order to evolve in the way we have seen through the different paths that can follow, needs to absorb light. So the photochemistry and spectroscopy are intimately related. And so if we consider what governs spectroscopy, we find that there are basically two selection rules that are directly related to UV-Vis spectroscopy. The first rule is the rule that everybody knows, that when an electron is excited, it cannot change its spin. That means that when you go from the ground state to the excited state, the first excited state the molecule will reach will be a singlet excited state, because the spin of the electron is not inverted. It will be inverted later on if the molecule evolves to a triplet state, but you cannot move directly from the ground state to an excited triplet state. not with the common absorption that we know. The second rule is as important as the first one. It is called the Laporte rule, and it states that the transition can occur only between states of opposite symmetry. This is somehow a bit not so clear to understand as the first rule, but simply this means that when we have a transition, this can occur only, for example, from a sigma orbital to a sigma star orbital, because these two orbitals, sigma and sigma star, have opposite symmetry. Or it can occur between a pi orbital and a pi star orbital. So an electron in a sigma orbital can be excited into a sigma star orbital, and an electron in the pi orbital can be excited into a pi star orbital. This is what the second selection rule says. But the second selection rule can be violated, and therefore also the electrons that are present in non-bonding orbitals, the n electrons, can be excited, even if there is no opposite symmetry of the orbitals. And so we can have some forbidden transitions, these are called forbidden transition, between the n orbital and the pi star orbital, or between the n orbital and the sigma star orbital. What is the difference between allowed and forbidden transitions? First of all, as you can see from this graph, the energy of a sigma and the sigma star orbital is very high. The energy between an n orbital and a pi star orbital is quite short. That means that the radiation that can induce each of these transitions can be different. And if we are looking for less energetic radiations, these will surely facilitate an n-pi star, or in some cases a pi-pi star transition, but not a sigma-sigma star transition that needs higher energy. But the second important thing is that if you want to distinguish between a allowed and a forbidden transition, you can see it by the molar coefficient. If you consider the Beer-Lambert law, this epsilon here is somehow telling how much your system will be able to absorb light. And this molar extinction coefficient is much smaller for forbidden transitions than for allowed transitions. So when these kind of transitions occur, the sigma-sigma star transition is, for example, typical of alkenes or all the molecules that possess only carbon and hydrogen bonds and only sigma bonds. But this transition, although could be potentially quite useful, is very energetic and usually falls below the limit of 200 nanometers. The limit of 200 nanometers is an important limit in photochemistry, because below this value, you have that oxygen can absorb, oxygen or the molecules in air can absorb. Therefore, photochemistry below 200 nanometer can be performed only in vacuum, not, for example, in a solution, but only in the gas phase. And therefore, this is not very simply achievable. So, more useful from a synthetic point of view are the other transitions, like the n-sigma star or the n-pi star, that are typical of molecules that possess unpaired electrons, so that possess heteroatoms like oxygen, nitrogen, sulfur. And the first ones are related to molecules that possess single bonds between carbon and oxygen, carbon and nitrogen, carbon and sulfur, while the second one, the n-pi star transition, is typical of compounds that possess double bonds. So, for example, as we will see in a few minutes, the carbonyl group. And finally, we have the pi-star transition that are typical of all the molecules that possess carbon-carbon bond, isolated carbon-carbon bond, and in this case we talk about ethylenic transitions, E-type transitions. Or we can have conjugated double bonds. In this case, we talk about K-type transitions. And finally, if we have aromatic rings, that are the most typical compounds that we see in this case, we will have the so-called benzenoid transitions that usually falls in a region of the UV spectrum that can be useful because it is above 200 nanometers, between 230 and 280. So, with this knowledge, let's analyze what happens when we excite a carbonyl group. The chemistry of the carbonyl group was one of the first that has been developed in the centuries, and still nowadays is one of the most proficuous ones because you can achieve many different transformations for exploiting the excitation of a carbonyl group present in a molecule. So, a carbonyl group has some pi electrons of the carbon-oxygen bond and some electrons on the two lone pairs on the oxygen atom. So, in principle, the carbonyl group can give two different types of transition: the pi-star transition and the n-pi-star transition. Taking back this scheme, the pi-star transition is the one characterized by the higher energy gap. That means that needs a radiation with higher energy, therefore with lower wavelength. The n-pi-star transition, on the other hand, is the one characterized by the lower energy gap, and therefore can achieved with radiations that falls about 300-350 nanometers. But another important thing to take into account is that the pi-star transition is an allowed transition, therefore the coefficient is higher. The n-pi-star transition, on the other hand, is forbidden, therefore the coefficient is quite low. So the absorbance in the case of the n-pi transition is quite low, but this is not really important from the point of view of the chemistry that can occur, because even if there is a low absorption, the reactions that can take place from a carbonyl group are very straightforward. So what happens when we have a n-pi-star transition? Basically, we have that one of the electrons on the lone pair on the oxygen atom is promoted into the pi-star transition. The pi-star transition can be described as a sum of two p orbitals, one on the carbon and one onto the oxygen. So you promote one electron from the n orbital to the pi-star orbital. But then another important feature of the carbonyl group is that it can easily give an intersystem crossing. In this case, the intersystem crossing is represented with a change of the spin of the electron in the n orbital. You could represent it also with a change in the spin of the electron in the pi-star orbital, because it is basically the same situation. The important thing is that this electron and this electron now have the same spin. So this electron cannot go directly back to the n orbital because we would violate the first rule. So the molecule, the carbonyl group in the excited state basically behaves as a diradical, because this electron and this electron with the same spin tend to stay as far apart as possible. Therefore, this electron will be localized onto the oxygen atom, and this electron that is in a pi-star orbital is somehow more close to the carbon atom rather than the oxygen atom. So these two electrons tend to stay apart from one from another. This means that we can consider the carbonyl group in the excited state as if it was a diradical species. So a diradical compound in the ground state and the carbonyl in the excited state more or less behave in the same way. And a diradical species also can be assimilated to a alkoxy radical. So the reactivity of this radical is similar to the reactivity of an alkoxy radical, again in the ground state. So we can assimilate the reactivity of a molecule in the excited state with a different molecule. An alkoxy radical is very much different from a carbonyl group, but a carboxy radical in the ground state. So what can an alkoxy radical give as typical reaction? An alkoxy radical can give a process that is called beta scission, as you can see here. So basically this oxygen here generates a double bond here, breaking one carbon-carbon bond, so making this scission here. Or it can give hydrogen atom transfer. So an alkoxy radical can take one hydrogen from the chain of the molecule, generating a new carbon radical. Or an alkoxy radical can also give addition to unsaturated double bonds, like alkenes. Also in this case, interacting with the pi electrons of the alkene and generating a new radical. So this is the chemistry of the alkoxy radical in the ground state. The carbonyl group can give similar reactions when excited in the n-pi star excited state. Let's see which are these kind of reactions. So if we talk about fragmentation reaction or hydrogen atom transfer reaction, so basically this beta scission or this hydrogen atom transfer, in this case, we talk about two very important reactions, quite old reactions, that are the Norrish type 1 reaction and the Norrish type 2 reaction. These two reactions are achieved by excitation with UV light of a carbonyl derivative. The carbonyl derivative is excited first in the ground state, then it reaches the triplet excited state. Then in the triplet excited state, we can assimilate this species as a diradical. And this diradical can give a beta scission, so breakage of this bond, making this acyl radical and this radical here. Then this molecule can evolve, losing, sorry, there is a mistake here, because this is not carbon dioxide, but carbon monoxide. So this molecule, this acyl radical here, can lose carbon monoxide, and therefore these two radicals can combine together. So basically you can perform a decarbonylation via this Norrish type 1 reaction. Synthetically, the Norrish type 2 reaction is more useful. In this case, we fall into the typical reactivity that we have called as the hydrogen atom transfer. When the carbonyl derivative has a hydrogen atom in this position, that is the gamma position, then you can have the transfer of this hydrogen atom from the carbon to the oxygen, generating this diradical here. This is a 1,4 diradical, 1,4 carbon diradical. This can evolve in two different ways. The first one is a cyclization. So from this compound, you can end up with a cyclobutane ring. This reaction is called the Young cyclization. Or alternatively, you can have a rearrangement that is similar to the McLafferty rearrangement that takes place, for example, in mass spectroscopy, in which you have that this bond here is broken and you generate these two fragments. So basically you can exploit these two reactions for different transformations. Here I just took from the literature some examples in which the potentiality of the Norrish type 1 and 2 reactions can be exploited, for example, for the synthesis of very, very complex molecules. And the complexity is achieved via the UV transformation. So these are multi-step reactions where the final molecule is elaborated through many different transformations, but the main complexity level is achieved via the photochemical processes. In this case, you have that this advanced intermediate here has a carbonyl group. The hydrogen can be extracted from here. You generate this species here. Then you have a single electron transfer with generation of a carbocation. And then you will end up with the formation of this polycyclic system that then will be elaborated further. Here another example, I will just skip because we are moving to the next important reaction of the carbonyl group, that is indeed the Paterno-Bucchi reaction that I mentioned before, discovered by Emanuele Paterno in 1909, but from a mechanistic point of view, it was discussed by a German chemist, Bucchi, in 1954. Therefore, this is why it is called the Paterno-Bucchi reaction. It is the formation of a four-member ring from a carbonyl and alkene, as we have mentioned, but it is not a concerted reaction. The reaction proceeds through the formation of a diradical between the interaction of the carbonyl derivative and the alkene. So let's focus a little bit again on the carbonyl in the excited state. In the carbonyl in the triplet excited state has one unpaired electron on the n orbital located onto the oxygen and one electron in the pi star orbital. Now this makes the pi star orbital nucleophilic, because it has one electron, and therefore this pi orbital can interact with electrophiles. On the other hand, oxygen has one electron less, and therefore it tends to react with nucleophiles. So you see that the reactivity of the carbonyl group in the excited state is completely reversed to the reactivity of the ground state. In the ground state, the carbon of the carbonyl is electrophilic and the oxygen is nucleophilic. In the excited state, you have the opposite situation. And this means that when the excited carbonyl interacts with an electron deficient alkene, then you have that the electron deficient alkene will interact with the electron in the pi star orbital. And therefore, the diradical that will be generated as intermediate, the final compound is always the occitan, but the diradical intermediate that is formed is different depending on the nature of the alkene. Electron deficient alkene will generate this as a consequence of the fact that it will be the pi star orbital that will interact with alkene, while when we have electron-rich alkenes, we will have that it will be the n orbital of the carbonyl derivative to interact. And therefore, the diradical that will be initially generated is this one here. The final compound is still, in both cases, an occitan, indeed. But the fact that the reaction proceeds through the formation of this diradical or this diradical has indeed some consequences, because, for example, from a stereochemical point of view, we might ask if the configuration of the alkene is preserved in the final occitan or not. And indeed, the chances that the configuration of the alkene is preserved are higher when the reaction proceeds through this mechanism, and are lower when the reaction proceeds with this mechanism here. Again, why this reaction is so powerful? Because there are so many important molecules in nature that possess this certain ring, and one possibility to generate this ring is indeed via the Paterno-Bucchi reaction. What happens? So let's move to another aspect. So what happens if the molecule we are talking about is not able to interact directly with light? Because, for example, if the absorbance is at too low wavelength, or because the molecule cannot directly generate a reactive species in the excited state. In these cases, we still can apply photochemistry because we can use photocatalyzers or sensitizers. The term photocatalyst or sensitizer is slightly different, but we do not have much time to describe this difference here. But what we can do is use a molecule that is able to absorb light and then transfer its excitement to the molecule we want to react. This can be performed through two different mechanisms that are described in physics, that are the first energy transfer, known as threat, and the Dexter energy transfer. The one we are more interested in is the Dexter energy transfer. Basically, we have our catalyst, our sensitizer, that is excited in the triplet excited state. So this molecule here takes one electron to the excited orbital. Then this Dexter energy transfer is basically a double electron transfer. So one electron is transferred from this orbital to this orbital, and one electron is transferred from this orbital to this orbital. So this molecule here, that in principle is not able to absorb light, via this interaction with the donor, will become excited and therefore will be able to give a reaction typical of photochemical processes. When do we use this approach? For example, one very important application of this is when we want to generate singlet oxygen. There are many photochemical transformations based on singlet oxygen. Singlet oxygen is a very peculiar molecule because oxygen in the ground state is very different from all the other molecules because is in the triplet state naturally. But when we excite oxygen, we transform the molecule in a singlet state. And in this case, the singlet state is highly reactive because in the singlet state, we have one full orbital and one completely empty orbital. So the molecule of oxygen in this state can behave at the same time as a nucleophile with this couple of electrons, as an electrophile with this empty orbital. And how we can obtain singlet oxygen? We can obtain singlet oxygen using a sensitizer that, through the Dexter mechanism, transform triplet oxygen into singlet oxygen. And once we get singlet oxygen, we can have many different transformations. For example, singlet oxygen can give cycloadditions with alkenes generating these dioxetanes, or with dienes generating these endoperoxides. Or, very important, it can give a reaction that is called Schenck-In reaction, in which peroxide is incorporated into an allylic moiety in this way. Or we can have also oxidation of heteroatoms like sulfur or phosphorus. So, for example, this chemistry here is very often used, for example, to destroy chemical weapons. And so the possibility of obtaining singlet oxygen through the use of a photosensitizer is very important. The Schenck-In reaction, that is one of the most important reactions, is a useful reaction. For example, in this case, I will not go into the complete mechanism, but we can see that with this reaction, we can trigger a cascade of events that finally transform a simple molecule that derives from citronellene to a very important antimalarian, that is artemisinin. All these steps here occur in one pot, triggered by the first event, that is a Schenck-In reaction, in which this allylic system is transformed into this allylic peroxide. And then from here, you have all the other events. I show this reaction in this point because then we will be back to this reaction in a while, in the final part of the presentation. Another possibility is to perform a photochemical reaction using a catalyst that is not able to transfer energy with the mechanisms we have just seen, but is able, for example, from the excited state to transfer electrons. We have seen that molecules in the excited state are stronger oxidants and stronger acids. So if we consider an excited molecule as a stronger oxidant, we can imagine some catalytic cycles in which the catalyst is excited, and then from the excited state it can either transfer one electron to the substrate, performing a reduction, or getting one electron from the substrate, performing an oxidation. And then the catalyst, that is in this case a radical cation, in this case a radical anion, through a second process in which usually an external molecule is used, is restored in the original state, because obviously in order to talk about the catalytic cycle, you need to restore the catalyst at the end. This chemistry, again, is very, very useful for two aspects. The first is that there are many reactions many radical reactions that can be performed in this way, just by generating by light some radical species that can behave then in different pathways, but also because in the recent decades, many of these catalysts have been elaborated in a way that simple visible radiation, blue or green, can be used for the excitement. So all the chemistry we have seen so far, the Norrish reactions, the Paterno-Bucchi reaction, usually occur under UV light, energetic UV light. The drawback of this is that the more energetic the radiation, the higher the chance to have also side reactions. If you can move from UV light to visible light, you have more selective processes. And by the use of these catalysts based on ruthenium or iridium, you can both reach very high potentials to perform a very wide option of different radical species, but also you can use very useful visible radiation. This ruthenium catalyst, that is one of the most used, is quite interesting in its behavior, because this is the catalyst in the ground state. The ruthenium is in the oxidation state too. When the molecule is excited, you have a process that is called metal to ligand charge transfer. That means that the electron that is promoted from the ground state orbital to the excited orbital moves from the metal to the ligands. So basically the molecule in the excited state possesses a ruthenium with the oxidation state free and a bipyridyl with an additional electron. So this molecule can behave both as an oxidant or a reductant, depending on which part of the molecule is used. So a ruthenium will tend to get one electron back, and therefore it will behave as an oxidant, while the ligands tend to give back the electron that they got, and so they will behave as reducing agents. And so, depending on the molecule you react this catalyst with, a molecule is able to accept or to donate electrons, the catalyst can work in both ways. So it is a very versatile process. Here we have one example in which the ruthenium catalyst is excited. Then, in this excited state, the ruthenium donates one electron to these diazonium salts, generating an aryl radical. The ruthenium then is formed in this state here, and will be restored by acquisition of one electron. Who is going to give the electron back to the ruthenium? It will be the molecule that will be evolved from the aryl radical, because the aryl radical reacts with an alkene that is present in the medium, and it generates a new radical, a sort of more reactive radical that is able to donate back the electron, generate the carbocation, and evolve to the final molecule. But the important feature is that this electron that is given back from this molecule is used by the ruthenium to get back to the ground state, and then it can start a new cycle again. A very important reaction that is used in this with this approach is the Giese reaction. That is basically a radical addition to an unsaturated system. You have a radical precursor where X can be many different things that once a photoredox catalyst interacts with this molecule, it generates the corresponding radical. And then this radical attacks the alpha-beta unsaturated system, and then the final product will be generated. So it is a radical conjugated reaction. This reaction is known occurring also in the ground state by using some radical initiators, but very conveniently can be performed using photoredox catalysis, because in this case you can just use the catalyst to induce the generation of the radical. And this is, again, one example in which the photochemical Giese reaction is used to synthesize a very complex molecule. And again, the key step in this multi-step reaction is the photochemical reaction. That is the one that is able to generate very easily high complexity. So let's move to the last part of this talk that is somehow related to the question. Photochemistry is very, very useful, but what about the use of photochemistry on large scale? Can I just use it in the lab, or should I consider it valuable also for industrial applications? Let's look at this time scale here. So in this time scale, we have two important points. 1834, the experiments of Tromsdorf on Santoni. 1912, this is a young Giacomo Ciamician, younger than the one we saw in the other picture, that in 1912 gave a speech at the International Symposium in New York. We will be back to this symposium later on. Then we have this period between 1940 and 1960, so roughly between 60 and 80 years ago. In this period, the first photochemical processes were implemented in an industrial scale. At that time, the caprolactam, that was the basis for making artificial fabrics like nylon, was made for the first time by a photochemical process. So the typical thermal reaction was replaced by a new photochemical process developed in Japan by Torayo, in which simple cyclohexane and nitrosyl chloride were irradiated, and the irradiation led to the formation of the caprolactam directly after the Beckmann rearrangement. So a very powerful reaction. Another important industrial process was the synthesis of this compound here, lindane, that was used very extensively as an herbicidal at that time, and that could be obtained by an exhaustive chlorination of benzene. Also in this case, the photochemical process developed in 1950 was very, very efficient. Then we have that the pharmaceutical company Roche and BAF that developed some camptothecin synthesis of these drugs. And in 1960, rose oxide, that is a fragrance used in parfums, was again implemented into an industrial process. So if 60 years ago there were these processes that could be performed on large scale, we would expect the industrial photochemistry to grow very, very rapidly until nowadays. This is not the case, because if we see from 1960 to 2009, there is a huge gap, and no more photochemical processes were implemented. The problem was a technical problem, because these reactions here that we have simply described are reactions that can be performed very, very easily with very simple equipment. But when you have to perform very precise photochemical reaction, then you didn't have in this period the sufficient technology knowledge to perform them. So the problem is essentially the fact that when you perform a reaction on large scale and the radiation comes from the outside, the Lambert-Beer radiation, the Lambert-Beer law tells that the light is very rapidly attenuated into the system. Let's consider this graph here. This is a solution of the ruthenium catalyst we have seen in the photoredox application. This is the distance from the wall of the recipient. So you have a solution, 2 millimolar of this ruthenium photocatalyst. 2 millimolar is quite high, but just to give you an example, this is a concentration of 2 millimolar, and this is the transmittance within the solution. After 0.5, after half millimeter, after half millimeter from the wall of the recipient, the solution is completely dark. So there is no more light. So how can you perform a reaction, for example, with thousands of liters of solution if the radiation after a very, very thin straight is no longer available for your molecules? This is the major delimitation of photochemistry on large scale. How to overcome this problem? The first solution that came in the early 2000 was the possibility to perform the reaction under continuous flow condition. This is a batch system where you have that only the molecules closer to the radiation are illuminated, and the others remain in the dark. And you might also have some... Sorry, are you saying something? I can't hear you. Sorry, are you talking? Can I keep going?
Yes, Professor, you can keep
Okay,
going.
sorry, I was hearing something there. Okay.
Just a gentle reminder for you for the presentation.
Yeah, I will soon conclude.
Okay, thank you very much. Keep going.
If you perform the reaction under a thin tube, like the one illustrated here, all the molecules are illuminated at the same time, and therefore the reaction is more efficient. Here you have, for example, a way to perform a photochemical reaction under flow conditions. You see, you have a tube that is wrapped around a lamp. You perform the fluid of the solution within this tube, and the reaction occurs with much higher efficiency. Here you have some other examples of flow systems that can be applied. The flow photochemistry is particularly important when you use, for example, gas reaction like the oxygenation reactions, because in this case you have that one major problem is the interaction between the liquid and the gaseous phase. But using flow chemistry and you performing this slug flow process where you have alternate solutions, little volumes of solution and gas, you have a much more efficient exchange between the two phases. And so you have different systems that can be used for these photooxygenation reactions. some are quite interesting because they apply some other knowledge, but the striking thing is that the efficiency of this flow, of this reaction under flow, is much higher than the same under batch conditions. So, for example, the same reaction here in batch, it takes 16 hours and only 20 minutes in flow. In this case, this transformation takes 1 hour in batch, but just 1 minute in flow. So flow chemistry is very, very efficient, but not only flow chemistry, because this is the plant where artemisinin is synthesized in an industrial plant. In this case, you have that the reaction is performed in batch in a very, very huge photoreactor where the illumination is from the inside. You see the size of the stirrer and the size of the lamps compared to the size of the person that is fixing it. So in order to achieve these technical advancements, we had to wait until these very years. And so it was not possible to do it in the 60s or 70s. So I have concluded. I would like to finally conclude this lecture with the words of Giacomo Ciamician, who said this in 1912 in New York, so more than 100 years ago. So basically, just to keep it short, he was saying that in the arid lands there will spring up industrial colonies without smoke and without smokestacks. So he imagined a world where forests of glass tubes will extend and will use photochemistry instead of fossil fuels. Is this something that is nowadays feasible? Not completely, but yes. In Spain, we have this solar synthesis of fine chemicals where we can perform very, very large scale photochemistry on a very large surface. So thank you very much. Sorry if I've been late, and I'm happy to answer to your questions if you have any.
All right. Thank you very much to Professor Dr. Andrea Basso for his very interesting and insightful presentation. Next, we will move on to the discussion and Q&A session. To manage our time efficiently, I will collect the first 3 questions first. Participants who would like to ask a question are welcome to raise their hand using the available feature or type their questions in the chat room. Please don't forget to write down your question in English. Professor Bass, I just couldn't help but notice what you're wearing today. Is that a MIPA UGM shirt that you're wearing? Okay. So now we have first one
So
is
why does the industrialization of artemisia require lamps with certain chemical elements that is in the houses? Well, the synthesis of artemisinin is quite interesting indeed, because the process that triggers everything is the generation of singlet oxygen. So it is not directly the molecule that is used that is able to absorb light, but there is a photosensitizer that is a tetraphenyl porphyrin. So the same molecule, I would say, that we have in our body in the heme or in other enzymes. So this porphyrin is able to absorb light in the visible region and in the green region of the UV spectrum, and then upon excitation porphyrin is able to interact with oxygen and generate singlet oxygen. So even if it would be necessary to use light that could interfere with other processes, the fact that we use a very mild radiation, green, blue is definitely milder than UV radiation, then you do not have any kind of side reactions. And the fact that once you perform the Schenck-Ine reaction on the advanced substrate, all the other processes occur spontaneously up to the final compound is indeed a very important feature, because otherwise the simple photochemical transformation would not be enough to make the whole synthesis so efficient. I don't know if I answered to the question or if there was something else.
Thank you very much, Prof. Basso, for the answer. Is that clear for Nurfianto Pangidum? Okay, so maybe there's no.
Okay.
Okay, that's clear. So we could get straight to the next question, maybe from Mr. Fahri Ashraf.
Hello.
Hello?
Can you hear me?
Yes.
Okay. So I have two questions. So if I'm not wrong, delocalization.
Not hearing very well now. I could try again.
About now?
Try to keep it a little bit closer to your mouth.
What
Yes,
about now?
that's fine.
Okay. So so if I'm not wrong, the delocalization of electrons in benzene is due to the interactions between pi and pi star. So when it eventually returns from pi star to pi, does the benzene radiate energy? And if so, wouldn't benzene continuously give out energy? And my second question is, in photocatalytic reactions, how important are the vibronic levels above S1?
Okay. First question. If you excite a aromatic ring using the benzenoid type transitions, you usually get indeed the promotion of one electron to the pi star orbital, and then benzene itself is not very useful from a photochemical point of view, in the sense that if you irradiate benzene, you do not have a very typical chemistry related to it. So the electron will move back to the pi star orbital, and then the reaction will, the photophysical, in this case, process will be just finished. So there is no other possibility. If you change the substrate from a benzene to a substituted benzene, then the substituent can play an important role. So, for example, if you have a benzene with a carbonyl group, so let's say benzaldehyde, for example, and in this case, the reactive part is the carbonyl group of the molecule, so the one that will let you perform the subsequent reactions. But if in the aromatic ring you have an electron donating group like a methoxy or a nitrogen atom, then this hydroxybenzaldehyde or methoxybenzaldehyde will have a reactivity that is completely different from the one we have seen, because in that case the pi star transition will be more favored. So the aromatic ring is not itself very important from a photochemical point of view, but it is important when you want to change the reactivity, for example, of other groups bound to the aromatic ring. The second question, indeed, we did not discuss about it, but when you have the excitation of a molecule from the ground state to the first electronic state, then you have that this electronic state is characterized by many different vibrational and rotational levels. And this obviously can affect the whole system, but it is more a photophysical process, in the sense that before going back to the ground state, the molecule might evolve to a different excited state, but a lower vibrational level. And then the consequence will be that the emitted light, after it goes back to the ground state, will have a lower energy content than the absorbed light. So absorption and emission do not occur at the same exact wavelength. But from a photochemical point of view, this is less important, because the property of the molecule changes independently on the vibrational and rotational level. As we have seen, for example, from the geometry of hydrogen cyanide, obviously, when you change from a linear molecule to an angular molecule, you might change all the vibrational parameters, but the most important thing is that the molecule is no longer linear.
Okay, so is that clear for Fahri Ashraf?
Yes.
Okay. So maybe for the next question from Alpha Hidayat, maybe you can turn on your mic. Yes.
No, you can hear.
Or if you have any problem with your micro video, so you can drop your question to the chat box.
Okay, there is one question in the chat box that is, how can we determine whether photocatalysts undergo oxidative quenching or reductive quenching? This is depending on the molecule you choose. So the fact is that the photocatalyst can perform either an oxidative or a reductive process, but if deciding why choosing one or another depends essentially on the redox potentials of the molecules you use to react with the photocatalyst. So the chemistry I have shown seems very simple, but in reality you need to study very deeply the redox potentials of all the species that are involved in the process, because you have to reach a complete match of all the potentials, both of the oxidation and reduction of the catalyst with the surrounding molecules, in order to be able to close the cycle.
Okay, so is that clear? Or we can just get straight for the last questions, if there's any. And a gentle reminder for all the participants. I'm so sorry. I beg your pardon because I forget to remind you regarding the attendant link that will be given at the end of this session. Don't forget to prepare your screenshot during today's session, to fulfill the requirements on the form. Thank you.
There is one more question.
Okay, maybe for the last. Yes.
What other wavelengths are used in photochemistry aside the UV region? Can visible light or infrared possible? Visible light, indeed. Actually, the modern photochemistry is moving to visible light. So when possible, the visible light should be used because of the advantages we have mentioned, the fact that it's less energetic and can give less side reactions. Obviously, infrared radiation alone cannot be used because the infrared radiation is not able to interact with the electronic states of the molecules. But the possibility of using infrared radiation is something that is being studied during these last years, because one thing we have not talked about is the possibility of using two photons instead of one. So basically we have that one photon is exciting one molecule, and the energy of the photon must match the energy, the difference in energy of the levels between the ground state and the excited state. But another possibility is to use two less energetic photons, and by the addition of the two energies, we reach the same energy of the molecule. So instead of using just one photon, we use two less energetic photons, and in this case, it is possible to use infrared radiation. The advantage of using infrared radiation is indeed that you use a radiation that is even less energetic, and so you might have even less possible side reactions. But it is, from a technical point of view, it is not so easy because you need, for example, lasers in order to do so. You cannot use a common light source like LEDs or mercury lamps.
Okay, so is that clear for Abdul Rahman? Okay, so what an amazing discussion for today's session, but because due to the time constraints, so we unfortunately cannot accommodate any more live questions as our Q&A session has come to an end. Or maybe for those whose questions weren't answered yet, if Professor Basso, if you don't mind, maybe
Sure.
the other uh the other participant who would like uh to give any questions through your email, maybe if you don't mind.
No problem at all.
It's no problem at all. So maybe you can just reach him out directly through his email, maybe if it's available, or you can ask to the committee if you need it. Okay, so
I have typed my email in the chat.
thank you very much for your kindness, Professor Basso. So if you really want to, maybe you know more deeper about uh this about the UV reactions or other relating materials regarding today's session, you can reach him out through his email. So, okay, to conclude today's session, allow me to present a brief summary. So, overall, photochemistry unlocks advanced chemical reactions by exciting molecules with light and fundamentally altering their physical and chemical properties compared to their ground states. While traditional methods relied heavily on high energy UV light that risk side reactions and substrate degradation, modern techniques have successfully shifted toward visible light photoredox catalysts mediated by organometallic photocatalysts like ruthenium and iridium. To overcome the classic bottleneck of scaling up for the chemical process, specifically the Lambert-Beer limit, where light fails to penetrate deeply into highly absorbing solutions in large batch reactors, flow chemistry has emerged as the definitive solution. By utilizing microfluidic and mesofluidic continuous flow system, light penetration is maximized, reaction efficiency increases, and the production of side product is significantly minimized. This technological leap has already achieved massive industrial success, notably in Sanofi's large-scale production of the anti-malarial drug artemisinin, and paves the way for a sustainable future driven directly by solar energy. Once again, Thank you very much, Professor Basso, for your exquisite materials today. So, as a sign of appreciation for the time, knowledge, and contributions shared with us today, we will now present a certificate to our guest speaker today.
Thank you very much.
Okay. We extend our deepest gratitude to Professor Dr. Andrea Basso for his willingness to share his valuable knowledge and experience during this event. We will take a photo with the certificate now. Okay, so is the photo? Okay, so before we start the barcode attendance, let's capture this moment with a group photo first. For those who aren't on camera yet, we invite all participants to turn on their camera so we can capture today's moment together.
Wait. Okay. Satu. Satu, 1, 2, 3. Next.
Is that all? Or
Finish.
okay. So once again, I remind you all the participants, don't forget to take a screenshot for today's event because the photo would be needed to fulfill the requirements for the form that is shared on the screen. So you can just scan the barcode on the screen to fill the attendance link, to fill the attendance form.
I can't hear you.
Okay, so
Yes.
before we ended today's session, we ask participants who had not yet submitted their attendance to fill out the attendance link that was shared in the chat or displayed on the screen. As mentioned at the beginning, certificates will only be given to participants who submit the attendance form. Please note that the data from this form will be printed on the certificate, so please ensure that your name and title are entered correctly. The speaker's presentation will be shared no later than 1 day after the event, so don't worry if you ask about the presentations. Before we knew it, we have reached the end of the event. Thank you very much to Professor Dr. Andrea Basso for sharing his knowledge and to all the participants who took the time to join us at today's case event. May the knowledge shared here brings benefits, broaden our horizons, and serve as inspiration for all of us. I am Gabriel Sumlak, your moderator, and I will now take my leave. I wish the very best of luck for you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you very much. Terima kasih.
Thank you very much, Prof. Basso, for your time.
Thank you.
Terima kasih untuk teman-teman, rekan-rekan yang sudah hadir juga bisa meninggalkan ruang Zoom.
200 grand later and we're not even working. Student loans worth more than what we're earning. Best lesson I learned is to keep on searching. Find your true passion and get to work. And better take action or you end up serving. Yeah, that's a fact. So you better clean up your act. So you better raise yourself a stack and tell the world they can suck on that. Don't come back, pack your bags. You take a trip and don't relax. You hit the switch and just attack. You find your niche and make some racks. Don't hold back. Everybody wake up. It's time to break up with the life you made up. It's time to trade up. Live the life you want now, a life you don't doubt. I could give a fuck how, just figure it out. Wake up, man, this life is a blur. Everyone's got an opinion, so which one you prefer? Cause I'll give you one that's coming from an entrepreneur. Don't give up on your dream if it's what you deserve. Failure ain't an option, so I'd be cautious. I hope that you're watching. Don't try to stop this, work until I'm nauseous. Cause I will not quit, no, because I want this. Don't try to stop me, failure ain't an option, so I'd be cautious. I hope that you're watching. Don't try to stop this.